Hi there. In this video, we're going to be going over horizontal asymptotes and end behavior. To start off, let's talk about horizontal asymptotes and what they are not. A horizontal asymptote is not a discontinuity. You may be used to hearing about vertical asymptotes, and you know that those are discontinuities in the graph. But a horizontal asymptote is not a discontinuity. What it is it describes what happened as x gets very large in either the positive or negative direction. It tells us where the y value is going. Or in other words, what is the limit to the y value? So we have a graph so that we can kind of analyze a little more what a horizontal asymptote is and connect it to end behavior. But before we do that, let's go ahead and look at some notation. So when we say as x becomes a very large positive number, the notation for that is as x approaches infinity. Or we can say, we can put the infinity symbol here, right? And then as x becomes a very large negative number, we can write that in symbols as x approaches negative infinity. That's a very large negative number. If you look at this graph here, we have the graph of a rational function. Now let's look at the right side. So on the right side, we have a branch of our rational function moving towards an x direction of positive infinity. And let's see, what is the function approaching? Well, as x moves towards positive infinity, notice that the y value is approaching 2. We can write that down here. This is our end behavior. As x approaches infinity, f of x approaches 2. Now let's look at the left side. Here we're looking at the bottom branch of our rational function. As x approaches negative infinity, what are the function values approaching? Well, if you continue along, notice that they get very close to, but they don't ever reach 2. So as x approaches negative infinity, f of x approaches 2. Another way we can word that is we can say that the limit of the function as x approaches positive or negative infinity is 2. We can just use a capital L to stand for limit. So the limit equals 2 on both sides. Also, this section is over horizontal asymptotes. Notice here this dotted line. This is our horizontal asymptote. The equation for the horizontal asymptote here is y equals 2. So we have a horizontal asymptote of y equals 2. So do you see here the connection between the end behavior and the horizontal asymptote? As x approaches positive infinity, f of x approaches 2. As x approaches negative infinity, f of x approaches 2, which makes our limit in both directions 2, and our horizontal asymptote is y equals 2. So the end behavior actually tells us what the limit is and what the horizontal asymptote is. Now that we've discussed what a horizontal asymptote is, let's go over the horizontal asymptote trick for rational functions, which helps us determine the location of horizontal asymptotes. The first part of this trick is to rewrite the function where you keep the highest power before factoring in both the numerator and the denominator. This is because as x gets very large, lower numbers have little effect. For example, if we have 3x cubed plus 2x minus 1 divided by 2x to the fourth minus 3x squared plus 2. Let's say you're trying to evaluate what happens at positive infinity. Well, you can't plug infinity in here because it's not a real number, but you can pick a really large number like, say, a trillion. Well, if I have 3 times a trillion cubed plus 2 times a trillion minus 1, that 2 times a trillion minus 1 is going to be way smaller than that 3 times a trillion cubed. So that relatively small value of 2x minus 1 can actually be canceled out when we go to evaluate the end behavior. The same thing in the denominator. If I have 2 times a trillion to the fourth minus 3 times a trillion squared plus 2, that 3 times a trillion squared plus 2 is going to have little effect compared to 2 times a trillion to the fourth power. So we can just ignore those last two terms when we're trying to evaluate what happens at infinity. So in doing that, what we'll have is approximately 3x cubed over 2x to the fourth when we're looking at the behavior at positive or negative infinity. Then we're told to simplify and use the following to determine the horizontal asymptote. So we're going to simplify it. If we simplify this, we get 3. We're going to put over 2 right here. Let's go ahead and put our 2 down here. We have x cubed over x to the fourth. We're going to cancel out the x cubed, and we're left with just 1x on the bottom. So that'll be 3 over 2x. So we just simplified it. And then it says we use the following to determine the horizontal asymptote. Well, we have 3 different scenarios here. The first one is if the degree of the denominator is higher than y equals 0 is the horizontal asymptote. So if we look at our rational function here, the approximation of it that we have, on the bottom, we have a first degree. We have x to the 1 right here. On the top, we don't have an x, so that's x to the 0, so we have a 0 degree. So notice that the degree of the denominator is higher. So for this one, our horizontal asymptote is going to be at y equals 0. So our horizontal asymptote is y equals 0. The other two scenarios are, the second one is if the degree is the same in both the numerator and denominator, then the ratio of the coefficients is the horizontal asymptote. And the third one, the third scenario is that if the degree of the numerator is 1 degree higher than the degree of the denominator, then there is no horizontal asymptote, but instead there is an oblique or slant asymptote. Now that you had a chance to learn about the horizontal asymptote trick in the last video, it's a good idea to get a basic understanding of why this trick works. Let's use an example to do that. So let's say that I have plus minus 1 over 100. What does that equal? That equals plus minus 0.01. What about plus minus 1 over 10,000? Well, that equals plus minus 0.0001. What about plus minus 1 over 1 million? That's plus minus 0.0000001. So you can see in decimal form a little more about what's happening as the denominator gets bigger. As the denominator gets larger and larger, what is the entire expression approaching? Well, we can say that it's approaching 0. The larger the number that you get on the bottom, the more zeros are going to be added behind the decimal point, and it's going to approach 0. So if you have infinity on the bottom, which means that you have an x left on the bottom that you're able to plug that large number into, then your asymptote is going to be y equals 0. Let's look at when we have very large numbers on the top. If I take plus minus 100 over 1, that's just plus minus 100. If I do plus minus 10,000 over 1, that's just plus minus 10,000. If I do plus minus 1 million over 1, that's just plus minus 1 million. So what happens when we have a very large number on the top? What is our function approaching? Our expression just keeps getting larger and larger. It's not approaching any number. It's just getting larger and larger. So when infinity is on top, then we can say that our function is approaching either positive or negative infinity.